Hello class, welcome to this video on AP Statistics, Chapter 7, Lesson 2, Sample Proportions. So what we want to do is we want to work with sampling distribution of proportions and the sampling distribution of the difference of proportions. And we want to be able to know how to work with those two. So learning target number 1, calculate the mean and standard deviation of the sampling distribution of p hat, interpret the standard deviation, and then we want to also, learning target 2, determine if the sampling distribution of p hat is approximately normal. Okay, so let's first define the sampling distribution of the sample proportion, p hat. Okay, so this is a distribution of values, as you see down here, down below. Distribution of values taken by the sample proportion p hat in all possible samples of the same size from the same population. Now this here, this graph that you see here, this distribution is taken from a penny activity, okay, from the book, in which they took pennies from, they took a pile of pennies, right, and they took 20 pennies at a time from that pile. And then from the 20 pennies that they randomly selected, of course, they identified the proportion of pennies that were in the 2000s, okay? And then once they got that percent or proportion, they plotted it as a p hat in this graph, okay? Now, this is an approximate sampling distribution, not an exact one, because for it to be exact, it would have to be in all possible samples of the same size from the same population, okay? And that's just not possible here, right? We only have so many possibilities. We don't have all the possibilities. All right, so the mean of this distribution, actually, if you are to calculate it, since this is approximately symmetric, you would see that the mean would be located approximately here, and that would be our mu p hat. Now, it turns out that the mu p hat is actually approximately, in this case, is approximately equal to the value of p, okay? And in the formula, the mu p hat is actually equal to p, okay? Exactly. In an exact sampling distribution of p hat. Okay, so the mean is simply the population proportion p. Okay, not to be confused with the sample proportion p hat, right? Those are two different things. Now, the standard deviation of the sampling distribution is given by the following formula. So we have sigma p hat. Now, this describes the spread of this distribution. And so the formula is the square root of p times 1 minus p divided by the sample size, n. So there's your formula for the standard deviation. Now there's you have to be careful because this formula is only applicable as long as the 10% condition is satisfied. Okay, so the 10% condition says that the sample size that I take has to be less than 10% of the population. Okay, so 0.10 times the population size, n, big N. Okay, so as long as it's less than 10% of the population, I can go ahead and use this formula. If it's not 10% of the population, then this formula is going to fall short. It's going to be smaller than the true value. Now, sigma p hat measures, if you wanted to interpret, it measures the typical distance between the sample proportion p hat and the population proportion p. Now, so that's the interpretation. So if I wanted to interpret sigma p hat, that's how I do that. Now, the sampling distribution of p hat is approximately normal. As you can see here, and this looks approximately normal, has that bell kind of shape, right? You can kind of see that. So it's approximately normal as long as the large counts condition is satisfied. Okay, so large counts condition says that n times p is greater than or equal to 10, n times 1 minus p is greater than or equal to 10 as well. Okay? All right, so let's kind of zoom in on this and focus on the left side here. So let's look at this example. So it says, suppose that 84% of students at a large high school regularly use a backpack to carry their books from class. So we got an 84%, so that's going to be the P. And then imagine taking an SRS of 100 students, so that's our N. so n is 100, and calculating the p-hat, which is the proportion of students in the sample who regularly use a backpack. So identify the mean. Okay, so the mean is mu p-hat is equal to p, which is the population proportion, which is 84%, or 0.84. Okay, so there's the mean. Pretty straightforward for that. Part B, calculate and interpret the standard deviation of the sampling distribution of p-hat. Verify that the 10% condition is met. Okay, remember we need the 10% condition in order to use that formula. Well, let's first calculate it. So we get sigma p-hat is the square root of p times 1 minus p over n. So we got square root of, if you may recall, p in this situation is 84%. Okay, so 0.84, and then we had a sample size of 100 students. So we got 0.84 times 1 minus 0.84. Okay, 1 minus 0.84 is 0.16. Divide that by 100 students, and we get a value of 0.0367. And so we want to interpret that. So what we're going to say is that in simple random samples of size 100, the sample proportion of students who regularly use a backpack will typically vary by about 0.0367 from the true proportion, or the true mean or true proportion of p, and then p was 0.84. Okay, so part 3 is the 10% condition. So remember, since this is taken from a large high school, we can assume that 100 students is less than 10% of the population of all students at the school. All right, so let's go ahead and describe the sampling distribution. So in order to determine if it's normal or not, we need to identify whether the large counts condition applies or not. Okay, is satisfied. Okay, so this is the large counts condition, n times p. So we have a sample size of 100 and a population proportion of 0.84. So that's going to give us 84, which is greater than or equal to 10. And then we're going to do n times 1 minus p. So that's 100 times 0.16, which is 16, which is greater than 10. Okay, so far so good. So that means that it is approximately normal since it passes. All right, so go ahead and pause the video and see if you can try the check. All right, hopefully you tried it, paused it, and we'll go ahead and identify the solution here. So in a congressional district, 55% of registered voters are Democrats. A polling organization selects a random sample of 500 registered voters from the district. Let p-hat equals the proportion of Democrats in the sample. Identify the mean. Okay, so we got mu p-hat, which is equal to p, which is the 55%. All right, and then we're going to calculate the standard deviation of that. So square root of p times 1 minus p. 1 minus p is 0.45 over n, sample size 500 registered voters. Sorry. Okay. To calculate that, we get 0.022. All right. So now we're gonna do the interpretation. So in simple random samples of size 500, the sample proportion of registered voters who are Democrats will typically vary by about 0.022 from the true proportion of p is 0.55. Okay, all right. And then last part of the check, so we can pause that if you want to try it. Okay, so let's go ahead and check the solution. So it's reasonable to assume that n equals 500. We're going to use a 10% condition, that it's less than 10% of all registered voters. Okay, so we're good with that. So it satisfies that. And then part C, describe the shape of the sampling distribution of p-hat. So again, we're going to do n times p. So we got 500 times 0.84. I think, well, was it 0.84? Was it 0.55? Oh, that's 0.55. Okay. All right. So we do that. So we get 500 times 0.55 is about 275 which is greater than or equal to 10, way bigger. N times 1 minus P, 500 times 0.45, which is 295. Wait, is it? So it's 225. Okay, not 295, but 225. All right, and so therefore it's approximately normal since it passes both checks. Okay, so approximately normal. All right, that's it for learning targets 1 and 2. So let's look at learning target 3. If appropriate, use a normal distribution to calculate the probabilities involving p hat. Okay, so this is why we try to determine if it's normal, approximately normal, so that we can do learning target 3. All right, so a polling organization asked a simple random sample, 1,500 first-year college students, how far away their home is. Suppose that 35% of all first-year students attend college within 50 miles of home. Find the probability that the random sample of 1,500 students will give a result within 2 percentage points of the true value. Okay, so we're going to say let p hat equals the true proportion, or the sample proportion, sorry, of all first-year college students who attended college within 50 miles of the home. And so we're going to calculate the mu p hat, which is p, which is 35%, 0.35. Okay, because that was given there. Now we're going to do the 10% condition. We're going to assume that the 1,500 from our sample is less than 10% of all first-year college students. Therefore, we can calculate the standard deviation, or use the standard deviation formula. Okay, the one that we discussed. So it's a square root of p times 1 minus p divided by n. All right, so in this case, p is 0.35, so 0.35 times 1 minus 0.35 is 0.65. Over n is just 1,500. Okay, 0.022. All right, now we're going to do the large counts condition to determine if it's approximately normal. So we have 1,500 times 0.35, which is 525, which is greater than or equal to 10, so that's good. We got 1,500 times 1 minus. All right, and then that's going to be 975, which is definitely bigger than 10. So classifying colors. Therefore, we can say that this distribution is approximately normal, okay? Okay, so it's approximately normal. So now let's go ahead and label it. So we're going to label the mean here, 0.35. We're going to label all the numbers. So we're going to add by 0.022 to the right and subtract 0.022 on the left, okay, to this. So if I do that, let's go ahead and add the 0.22 first. So actually, we'll round it to about 0.023, maybe perhaps, okay? All right, so in that case, it's going to be 3. Okay, so it should actually say 0.0123 right here. So apologize for that. Okay, so then we'll go ahead and do that here. So 0.0123. So it's going to be 0.3623. And then we got 0.3746. And then here 0.3896. Now we're going to subtract 0.0123. 0.3377. 0.3254, and then lastly 0.3131. All right, so that's that, and then we're going to do so we want it to be within 2 percentage points, right? According to what it's saying here, within 2 percentage points of the true value of 35, okay? So really what they want is they want it to be 2% of 35 is 37%, okay? So they want the p hat to be 0.35 plus 0.02, and then 0.35 minus 0.02, right? Within 2 percentage points. So it's going to be between 0.33 and 0.37. Okay, so those are our two values. So 0.37. Okay, and then we got the other side of that. Okay. And it says within. So that means we're going to shade in between. All right, so that's our shaded region. So we can, what we're going to do is we're going to use a calculator and the z-score. So let's write down the formula for the z-score. Let's do it over here. Okay, so z-score is remember the z-score is value minus mean divided by the standard deviation. Now the value is p hat. The mean is mu p hat. And the standard deviation is sigma p hat. Now remember that mu p hat is equal to p. So it's really p hat minus p divided by sigma p hat. Okay? So we have here p hat, which is, well, we're going to calculate two z-scores, right? So one of the p hats is going to be the 0.33. The other one's going to be 0.37. Okay? So let's do that. So 0.33, excuse me. Okay, so 0.33 minus 0.35 over, that's the mean, the p is 0.35, and then the sigma p hat we calculated 0.0123. So you should get about negative 1.63. Okay. Now we're going to do the 0.37 minus 0.35 over 0.0123, which is about 1.63. Right. So we want the p hat to be between 0.33 and 0.37, so the probability of that, which is the same thing as saying the probability that the z-score is between negative 1.63 and positive 1.63, right? Those are the two z-scores. All right, so these are equivalent. Now, we're going to, in order to find use the table, we're going to look at the table for 1.63, negative 1.63, and subtract those two values, all right? So that's what we're going to do. So let's do negative 1.63 first, positive. Okay, so we got 1.6, 0, 1, 2, 3. So yeah, 1.63. So that's 0.9484. Okay, so we got 0.9484, and then the next one, negative 1.63. So negative 1.63. Oh, let's say 1.4, negative 1.6, and then 3, 0.0516. Okay, so we're going to subtract those two values and see what we get. Okay, so it was 0.9484 minus 0.0516. So we subtract that to 0.8968. There you go. So that's the probability. All right, so now if we want to do the calculator, this is why we have this area. So the lower is 0.33, the upper is 0.37. We got our mean of 0.35. And standard deviation, 0.0123. So if you did that, you get about point. Okay, if we do that, we get 0.8961, which is pretty darn close to what we got here, 0.8968. Okay, so go ahead and pause the video and see if you can try the check. All right, so let's go and take a look at it. So Harley-Davidson motorcycles make up 14% of all motorcycles registered in the United States. So 14%. You plan to review a simple random sample of 500 motorcycle owners. How likely is it to contain 20% or more who own Harleys? So we're going to say P hat is the sample proportion of those who are Harleys, right, of all the registered ones. So the sample proportion. And so mu P hat is equal to P, which is 0.14. Okay, so that's my P. Assume that the 500 that we took is less than 10% of all registered motorcycles. Therefore, we can calculate this. So we're going to do P hat, or P times 1 minus P. So 0.14 times 0.86 over 500. So we get 0.0155. Okay, so now we're going to do large counts condition. So we got 500 times 0.14 is equal to 70, which is greater than 10, so that's good. And then here we got 500 times 1 minus that, so 0.86. That's going to give you 430, which is greater than 10, so good. Therefore, it's approximately normal. All right. So since it's approximately normal, we should be able to label the numbers there. So again, the middle is going to be the P, which is 0.14. The standard deviation, if you recall, is is up here, 0.0155. Okay, so we're gonna add those all up. So to 0.155 to this. Okay, so it's gonna be 0.1555, 0.171, and then 0.1855. Okay, and the numbers on the left: 0.1245, 0.109, and 0.0935. Okay, and we want the p hat to be greater than 20%. Okay, so it's a really tiny portion of the curve, as you can see. All right, remember, if I want to do area on the right, I need to take the area on the left, subtract it from 1. Okay, so we're going to calculate the z-score. Remember, is p hat, which is 0.20, minus the p, which is 0.14, divided by the standard deviation, which is 0.0155. So if I calculate that, I get about 3.87. Okay, we don't need this part. We don't need to do 2 z-scores. We only need to do 1 z-score. So typo. All right, so the probability that p hat is greater than or equal to 0.20 is equal to, we're going to do 1 minus, and then we're going to look up points 20, okay? So 0.20 right here, 0.5793. So 1 minus 0.5793. Oh, oops, sorry. This should be the z-score. So we're going to look at 3.87. I'm sorry. So 3.87. Let's go to that. Now, oh, look at this. So notice that the biggest is 3.49. So anything above 3.49, like 3.5, 3.6, 3.7, 3.8, like what we got, you're just going to say that it's 0.999, okay, for the area. So that's what we're going to say. So we're going to say that this area on the left is 0.9999. And then if I subtract that from 1, I get about 0.0001. So, such a tiny probability. Okay, you're going to get the same thing if you do normal CDF. So the lower is 0.20, the upper is infinity, or really big number, or 1,000. The mean is 0.14, the standard deviation is 0.0155, and as a result, you get 0.0001. Okay? All right, so let's look at the next learning target. All right, so learning target 4, calculate the mean and standard deviation of the sampling distribution for p hat 1 minus p hat 2, and interpret the standard deviation, and then determine the sampling distribution if it's normal. Okay, so so if I have a distribution, sampling distribution of p hat 1 minus p hat 2, the mean of that is going to be p1 minus p2. Okay, this is going to be our formula. All right, now the standard deviation is going to be as follows: the square root p1 times 1 minus p1 over n1. Remember, this is what we had for the sigma p hat. But since we have a p minus p hat 2, we're going to include another term, right? Which includes the p2 terms. p2, 1 minus p2 over n2. All right, so this is our formula for that. Okay, now the standard, remember this, just like in the previous learning target with the standard deviation for p hat, this formula only applies as long as the 10% condition is satisfied. So it has to be satisfied for both samples. So N1 has to be less than 10% of the population of the first population, and N2, the sample size for the second population has to be smaller than 10% of that second population. Okay. All right, now there are 2 types of independence for this formula, okay? Because now we have 2 samples, right, or 2 different populations. So, so that means that there are 2 types of independence now. The first one is the fact that these samples here are independent. So N1, N2, those are independent samples that we took. And so between themselves, they're independent, and therefore we can add the variances, right? That's why we have a plus sign right here, because we're adding the variances for this, for sigma, okay? So then within each sample size, so like for example, within the first sample size or within the first sample, there's also independence as well, meaning the observations within each sample are independent. Okay, um, so that's important to understand. So you have independence. So let's say these are your two samples, right? Um, let's just say these are your two samples, 1 and 2, just as an illustration. So you have independence between the samples, but you also have independence within the sample itself, between the observations in the sample. Okay. Um, let's say you have an observation here and an observation here. You have independence within those observations. Okay, so in between them. So that's important. Two types of independence. And so for this one, when you're sampling without replacement, um, the actual value of the standard deviation is smaller than what the formula suggests, right? But if the 10% condition is met, then the difference is negligible. So the 10% condition is used to meet the second independent condition, not the first, okay? Um, so it's important to understand that. Now, we need both of these in order to use this formula, because you have to have independence between them, which is why we have this plus sign in between these two. But you also have to have the 10% condition met to even use this formula to begin with. Okay, that's important to understand. You need these two things in order for that standard deviation formula to be valid. Okay. All right. Now, what does this sigma measure? Well, it measures this. It measures the typical distance between this, right, the p hat 1 minus p hat 2, and the true value, the true difference, p1 minus p2. Okay, so we have the typical distance between the sample differences and the true differences, okay, in the proportions. Now, the sampling distribution of p hat is approximately normal as long as the large counts condition is met. All right, so this time you have 4 different conditions you have to test, right? 2 for each. Rather, we had 2 earlier because we only had 1 sample, right? Now we have 2 different independent samples. All right, so N1P1 is greater than or equal to 10. This is greater than 10, this is greater than 10, and this is greater than 10. Okay, so we got to check 4 things. All right, so now let's look at example 3. Suppose there are 2 large high schools, each with more than 2,000 students. Okay, so 2 large high schools, more than 2,000 students in a certain town. At school 1, 70% of the students did their homework last night. Okay, so that means P1. Okay, so they already told us P1 is 0.70. Only 50% of the students at school 2 did their homework last night, so there's your P2. The counselor at school 1 selects a simple random sample of 100 and records the proportion P1, okay? And then skill count 2 counselors for 200 students. Okay, so what is the shape? So we're going to verify that the large counts condition is met for both samples, right? Okay, so N1 times P1. Okay, so we got 100 for the first sample times 0.70 for P1. So that's going to be 70 counts, which is greater than or equal to 10. And we'll do this for the rest of the N1. So 100 for this one, and then 1 minus 0.70 is 0.30, which is 30 greater than 10. Okay, good. And then for the second sample, we had 200, and then the proportion was 0.50, which is going to be 100, which is, of course, greater than 10. And then we have 200 times 1 minus 0.5, which is the same thing as still 0.5. So it's still going to be 100 greater than 10. All right. Good. So therefore, it has to be approximately normal, right? All right. Awesome. So now let's look at the mean. So the mean, remember, if you recall, is equal to P1 minus P2. So in this case, we have 0.70 minus 0.50. which is equal to 0.20. All right, and then calculate, interpret, and standard deviation, and then verify 10% condition is met. All right, so let's do the 10% condition first. The first sample, which is 100, is we're going to assume that that's less than 10% of all students at the large high school. And let's see if that's true. So we have 100 for our sample size, but we had more than 2,000 students at the school. So at minimum, this percent is going to be, let's see, about 20. Yeah, so minimum is going to be 5%, as, or at maximum rather. So the maximum is going to be as 5%, but either way, it's going to be less than 10%, right? So that's true. So that's a check. Now this one, we're assuming that this one's going to be 10% of all students at the school, but we could test it out. We had 200 students at the school, over 2,000. Even if we had that, right, we would have 1 over 10, which is 10%, right? Now, it's going to still be less than 10% because this number is actually greater than 2,000, okay? So therefore, this is going to be less than 10%. Okay, so if you look at it, it says more than 2,000 students, right? So that's important. So it does technically meet that cutoff, so we're good. All right. Okay, so now sigma p hat 1 minus p hat 2. Again, the formula we had the formula earlier, but we're just gonna I'll go ahead and apply it. Okay, so square root p1 times p1 minus p1. Okay, so 0.70 times 1 minus 0.70, which is 0.30, over 100 plus p2, which is 0.50 times 1 minus p2. Again, it's another 0.50 over 200. It's going to give you roughly 0.058. All right, so interpret this is like the interpretation of this is that the difference in the sample proportions, p hat 1 minus p hat 2, of students who did homework typically varies by about 0.058 from the true difference of proportions of 0.20. Okay, all right, so that's the interpretation. Let's go look at the next problem. So go ahead and pause and see if you can attempt this problem through all the way to C here, so you can see it. All right, hopefully you paused and tried it, and let's go ahead and take a look. So your teacher brings 2 bags of colored goldfish to class. Bag 1 has 25% red crackers, and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes a simple random size of 50 crackers from bag 1 and a simple random sample of 40 crackers from bag 2. Let p hat 1 minus p hat 2 be the difference in the sample proportions of red crackers. What is the shape? Okay, so let's write down what we have. We have N1, which is 50 crackers from bag 1, which has a proportion of 25% red crackers, 0.25. Then you have a sample size, simple random sample of size 50 crackers, or no, 40, sorry, from bag 2 with a proportion of 35% red crackers. Okay, so now we can apply this to both. So we got 50 times 0.25. Okay, so about a quarter of 0.25 is going to be about 12 and a half. Okay, so 12.5, which is greater than 10. Okay, good. And then 50 times 1 minus, so it's going to be 3/4, 0.75, which is going to be 37 and a half, which is greater than 10. All right, so now for the sample 2, we had 40 of them, and with a probability 0.35, which is going to be 14, which is greater than 10. Good. 40 times 1 minus, which is 0.65, is 26, which is greater than 10. All right, so therefore, it's approximately normal. Okay, so we're good with that. So it passes the large counts condition. Now we're going to find the mean. So the mean remember it's going to be p hat 1 or p1 minus p2. So it's going to be the red crackers from bag 1 minus the proportion of red crackers from bag 2. So in this case, when we do bag 1 is 25% and bag 2 was 35%, right? So we're going to subtract those. 0.25 minus 0.35, which is negative 0.10. So it's okay to get a negative mean of proportions here, okay? Because you can get a negative difference. That's fine. All right, so now calculate and interpret the standard deviation. Again, let's do the 10% condition. So the sample size 1, which is 50 crackers, it's going to be less than 10% of all colored goldfish crackers in bag 1. So remember that it says that there were more than 1,000 crackers, okay? So we're going to say that we had a sample size of 50 over 1,000. Now it's more than 1,000, right? Technically here. So if it's more than 1,000, well, what's 50? What's 50 divided by 1,000? So let's do that real quick. 50 divided by 1,000. So that's 5%. And so this value, which is where the 1,000, where it's actually greater than 1,000 here, is actually going to be less than 5%. There, and which is therefore less than 10%. So good. Now for this one, it was 40 crackers. So 40 over 1,000, which was technically greater than 1,000. So this is going to be less than 4%, which is less than 10%. Okay. All right, so this is definitely going to work as well. All right, so we're good to go. We can do the standard deviation formula. So we have P1. P1 was 0.25. 1 minus P1 is 0.75. And then we had 50 crackers for that sample size. And then 0.35 for bag 2. 1 minus 0.35 is 0.65. And then we had 40 crackers there. So this is going to give us a standard deviation, 0.0971. All right. So we didn't get a chance to do the interpretation. So we can go ahead and write it down. We can go ahead and write it down here. That's fine. And we'll interpret what the standard deviation means. Okay, so let's go ahead and interpret. I'll put it over here, I guess, since we're low on room. All right, so the difference in sample portions of red crackers typically varies by about 0.0971 from the true difference of negative 0.10. True difference in proportions, I guess you can say, of negative 0.9, but that's fine. We can do it like that. All right. So there you go. So that's your interpretation. Okay. All right. So learning target number 6. If appropriate, we want to determine if we can calculate probabilities involving p hat 1 minus p hat 2. All right. So let's go ahead and take a look at this. So for example 4, using the example earlier, which is what we just did, the goldfish crackers, estimate the probability that the proportion of red crackers in the sample from bag 1 is greater than the proportion of crackers in the sample from bag 2. Okay, so, and we're going to continue that on the other side here. Okay, so we know it's a normal distribution. So let's go ahead and label our normal distribution. The x-axis, or the axis is labeled here for this graph, which is p hat 1 minus p hat 2. That's what this axis represents, which is the difference in proportions I should say proportions, sorry about that, of red crackers in bag 1 and 2. All right, so we know that the center is going to be the mean, which is negative 0.10. That's what we calculated earlier. And it's going to go by the standard deviation of 0.0971. So I'm going to go ahead and add that to get the other numbers. So again, I'm adding 0.0971. Okay, this is 0.1913. I'm going to subtract 0.091. So it's going to be negative 0.1971. And then the next one's going to be negative 0.2942 and negative 0.3913. Let me rewrite this number. Negative 0.2942. 2942. All right. So the p hat one minus p hat 2. We want to see if we go to the back to the original problem. It says we want the proportion of red crackers in bag 1 to be greater than for bag 2. So that means let's interpret what that means. We want p hat 1 to be greater than p hat 2, right? And if that's true, then what we can say is that this is the same thing as saying p hat 1 minus p hat 2 is greater than 0. Okay, that's basically an equivalent statement. So this is why we graph p hat 1 minus p hat 2 here, and we want that to be greater than 0. So 0 is around here. Okay, so this is going to be p hat 1 minus p hat 2 is equal to 0. And we want to shade to the right of that because it's going to be greater than that. Okay, there you go. Now let's calculate the z. So remember that the z is equal to the value minus the mean divided by the standard deviation. Now what's the value here? The value is p hat 1 minus p hat 2, right? And the mean is the mu p hat 1 minus p hat 2, right? And the standard deviation is, well, the sigma p hat 1 minus p hat 2. So if I were to continue to write the formula, well, we know that we know the value. It's going to be the same. But the mean of p hat 1 minus p hat 2, remember, is p1 minus p2, right? Over, and then this, we know what that formula is. It's that square root formula, right? That complicated square root formula. Which is the square root of p1, yeah, that whole thing. Okay, but I won't write it here. So we know what that formula looks like. We'll calculate that in a second if we haven't already. Oh, we calculated this already, so we can just plug it in. But this is your formula for the z, all right? For this difference in proportions. So let's go and calculate it. What's p hat 1 minus p hat 2? It's 0, right? That's the value that we're looking for. So 0 minus the value that they're asking for. And then p1 minus p2, that's the negative 0.10. So we have 0 minus negative 0.10. Okay? So it turns to a double negative, which is positive, right? All right, so over the sigma, remember we said it was 0.0971. All right, so this double negative turns into a positive, and so you're going to get positive 1.03 approximately for the z. All right, so we want the probability that p hat 1 minus p hat 2 is greater than 0, or the probability that z is greater than 1.03. They're equivalent. Remember, if you want the area to the right, you need to subtract the area 1, or you got to subtract the area from the left from 1. Okay, so 1 minus, and then we're going to look at this up on the table. Right, so 1.03, yeah, 1.03, which is 0.8485. Okay, 0.8485. Okay, so 0.8485, 1 minus that is 0.1515. There you go. That's the probability. We could also do this in the calculator. So the lower region is 0. The upper is infinity, or a big number. So say 1,000. The mean is negative 0.10. The standard deviation is 0.0971. And if you did that, you would get a similar result. You could get the same result here. All right, so go ahead and pause the video and see if you can attempt the check. All right, hopefully you did part A. Let me go ahead and show you part B here. All right, so I showed you the parts A through D. So let's go ahead and to solve this. A researcher reports that 80% of high school graduates, but only 40% of high school dropouts would pass a basic literacy test. Okay, we got 80% graduates and then 40% dropouts would pass a basic literacy test. We could ignore this 7 here. Assume that the researcher's claim is true. Suppose we give a basic literacy test to a random sample of 60 high school graduates and an independent random sample of 75 high school dropouts. Let p hat, this should say G for graduate, so not C, so I apologize for that. So let's go ahead and change that. So this is going to be G, it's going to be G, G for graduate, and D for dropout. Okay. All right, so yeah, so what is the shape of the distribution p hat G minus p hat D, and why? So let's use a large counts condition. Let's label what we know. There are the sample size for the graduates is 60. The p for G is 80% for graduates, and then the proportion for the sample size for the dropouts 75, and the proportion for dropouts is 40% right here, right? All right, so let's plug it in. So we got 60 times 0.80, which is 48, which is greater than 10, so that's good. Let's do it again for the graduates. So 60 times 1 minus 0.80 is 0.20. Okay, let me write that a little bit better. All right, and that's going to give you 12, which is greater than or equal to 10. All right, now let's do dropouts. So 75 times the probability is 0.40, which is going to be 30, which is greater than 10. And then again, so 1 minus is going to be 0.60, it's going to be 45, sorry. Which is greater than 10. Let me double check that. Just want to double check that number. Make sure that's right. Okay, 45. Still want to double check. All right, so it's greater than 10. All right, so our conclusion is that the distribution is approximately normal, okay, for the shape of the sampling distribution. All right, so that's part A. Part B, find the mean of the sampling distribution. Again, this should say a G, of course. Let me put a G for all these. All right, so find the mean. So it's going to be PG minus PD, which is 0.80 minus 0.40, which is 0.40. Okay, that's it. Now, verified 10% condition, we're saying the number of graduates, recall, is 60. So, and it's, in this case, it says, yeah, so we're going to assume that's 60, right? So we're going to just put 60. So this is 60, which is less than 10% of all high school graduates. That's pretty reasonable. All high school graduates? Yeah, there's probably a lot of high school graduates just throughout in general. So that makes sense. That's reasonable. And we say the number of dropouts, which was 75 from our sample size, is less than 10% of all high school dropouts. Okay, so those are two reasonable assumptions to make. So check. Therefore, we can proceed. standard deviation. So the square root of proportion of graduates, what was 0.80 times 1 minus 0.80 is 0.20 over 60 of them. Proportion of dropouts, 0.60, 1 or 0.40, and 1 minus 0.40 is 0.60 over 75 of them. So this gives you standard deviation. Let's see, it's roughly 0.0766. And I'm going to show you how to put this on the calculator, just in case you need a refresher on that. Okay, so let's go ahead and plug it in. So we got, so we're going to do the square root, so second x squared, and then we got 0.8 times 0.2 divided by 60 plus 0.4 times 0.6 divided by 75. Enter, and you go 0.0766. All right, so let's do part D. Find the probability that the proportion of graduates who pass the test. Oh, and we didn't, we did interpretation, so let's do the interpretation. Sorry about that. So let's interpret that. Okay, so let's interpret that over here, just because we have a little more room here. Okay, so we're going to say the difference in the sample proportions of, now let's look at the original problem. This is for um, of high schoolers who would pass a basic literacy test. Okay, basic literacy test. The difference in sample proportions of high schoolers uh, and then we're going to say graduates minus dropouts who would pass a basic literacy test typically varies by about 0.0766 from the true difference in proportions of 0.40. Okay? All right, so hopefully that made sense. Again, we're interpreting it the same way. The only difference is the context in which we're interpreting it. Okay? All right, so let's go ahead and look at part D. So find the probability that the proportion of graduates who pass the test is at most 0.20 higher than the proportions. Okay, so graduates, then the proportion of dropouts. Okay, so they're basically saying that the at most means it's less than or equal to. So this means less than or equal to. Okay, so they want p hat g minus p hat d to be at most less than or equal to 0.20. So that's what they want. So let's label this here. This should say a g again. All right, so the mean, remember, was 0.40, and the standard deviation was 0.0766. So I'm going to be adding that here. So this is the next one is 0.5532, and then the last one is 0.6298. Now I'm going to subtract on the left side. And we're going to label our points 20. We want it to be less than or equal to, like that. All right, so let's calculate the z. Remember that the z is, in this case, is going to be p hat g minus p hat d minus pg minus pd over sigma p hat g minus p hat sub d. Right, so we're going to use that formula. So z, the p hat g minus p hat d, the value is 0.20 minus the mean is 0.40 over standard deviation, which is 0.0766, right? And so that's going to be about negative 2.61. Now, this is the area on the left side. The table gives us the area on the left side by default, so we only have to look that up to get our answer, okay? So this is another G. So we want this to be less than or equal to 0.20, the probability of that. And let's go ahead and look up negative 2.61 on our table. So we got some negatives, 2.61. 2.61. So there you go, 0.0045. And it already gives you the area to the left, according to the table. All right, so 0.0045. Okay, so 0.0045. We don't need the rest of this, so I'm just going to cross that out. All right, so there you go. So this is our answer. Let's do the calculator. If we use the normal CDF function, the lower is negative infinity, so we're going to put negative 1,000, negative big number, and then upper 0.20. The mean is 0.40. Standard deviation is 0.0766. And so you get about 0.0045. All right, guys, that's going to do it for the video. Hope you found this useful and informative. And as usual, I'll see you in the next one.